Hello, here's another circuit analysis question. This time we've got a bit with variable resistors in there because it comes up quite a lot. You know, so many circuits that are built in real life have variable resistance in them, so it's worth having a look at one. This circuit is pretty straightforward. We've got a thermistor and a fixed resistor connected in series to a 24-volt EMF. And the switch gets closed. The voltmeter that's across the fixed resistor initially measures is 8 volts here. So we need to then do some very basic circuit analysis here. So calculate the current in the circuit first of all. You know, it's a series circuit, so we got the same current all the way around. So we can just look at the current through this fixed resistor. So that's going to be the voltage divided by the resistance. That's our V equals IR rearranged. So I is the voltage, our potential difference divided by the resistance, which is then 8 divided by 200. So that is 0.04 amps. That's what we got running around everywhere. Then we need the potential difference across the thermistor. Well, Kirchhoff's second law helps here because we know that the potential differences have to add up to the EMF. So if we've got 8 across the fixed resistor, we must have 16 across the thermistor, so they add up to the 24 EMF that we've got. What is the resistance of the thermistor? Well, the PDs get split in proportion to the resistances. So if our voltages are split 2 to 1, our resistances must be split 2 to 1. So we must have 400 ohms across as a resistance of the thermistor. And then what is the power dissipated in the thermistor? Well, we can do an I squared R, or we can do a V squared over R, which I think is going to be maybe slightly easier numbers. Actually, it's all the same, really. We're going to have a 64 in there somewhere. So anyway, we've got 256 divided by 400, so that's 0.64, isn't it, watts? You'd have got the same because we're going to have... you could have squared that and multiplied by 400, you still get the same thing. So simple circuit analysis, but the last two parts of the question just flesh this out a little bit, because we have loads of variable resistance setups in circuits. You know, okay, we've got a thermistor here, but we could have like dependent resistor. We could have, you know, your classic what am I doing? What am I trying to draw out here? A classic variable resistor, you know, the ones where you've got like a fly lead on or something like that. So all we're doing is changing these ratios here of resistances, which then changes our ratios of potential differences. So if you've then got a resistor which is changing, we've got something else there which is fixed, and then we've got a connection point here, then okay, let's actually just go back to this being a thermistor, so I don't have an easier circuit to draw. We're changing this potential difference across the connection point just by changing the resistance of that. So this comes up in loads of different places, whether we're doing sensing, which is quite often what we're doing with light dependent resistors and thermistors, or whether we've got some kind of, you know, dial, whether it's a dimmer switch on a light or a volume dial or something like that on an amp. Yeah, this is all we're doing. We're just changing this split in resistances, this ratio. So we're changing our ratio of potential differences. Right, so what are we actually doing here in part B? We've got a few minutes after closing the switch, the voltmeter reading has risen to a steady value of 12 volts. The value of the fixed resistor remains at 200 ohms. Explain why the potential difference across the fixed resistor has increased. So, right, we've got one of these chains of reasoning. So we want to say that the temperature of the thermistor has gone up. So that's the first thing. Then we can say, so therefore the resistance would have gone down. Therefore, the PD would have gone down on the thermistor. Therefore, the PD would have gone up on the fixed resistor. So it's just one of those simple chains that we have. But it's a nice way to set it out then when you're writing it as an exam answer, because these are all just, well, more or less half sentences that you can just write one line after another, each step following from the previous one. Explain why the resistance of the thermistor must now be 200 ohms. Well, we can say that the PD is split in proportion to resistance. So if we've got 12 to 12, therefore we must have 200 to 200. So that's our voltage, that's our resistance. So that is all good. Then the last part, we got a bit of a sketch going on here. I mean, I've sort of cluttered up the axes a bit now by writing the previous answers. But I want us to sketch possible IV characteristics for the fixed resistor and the thermistor. Now, the fixed resistor, we could, I mean, it does say possible, but let's assume that we've got an actual ohmic resistor here, which means we're going to have a straight line going through the origin. We've also got some fixed points in that we know that it has to go through, what was it, 0.04 amps at a voltage of 8 volts. So 8 volts, 0.04. So it's got to go through that point and that point, which means we're going to get straight line through the origin going up there. So remember with Ohm's law isn't just saying, oh yeah, V equals IR. V equals IR applies all of the time. The important thing with Ohm's law is saying that R is a constant. We've got a constant there of proportionality. So however we're changing the current or the voltage, whichever one we're trying to manipulate, we're going to have the same resistance, i.e. the gradient of this line is unchanged. That's what Ohm's law is tapping into. So if we then drew out the IV characteristic for the thermistor, and we know on this one that it will, what have we got? If it's got 12 volts across it, then we've got 0.06, because we could redo this calculation here for the whole circuit and say that we'd have a total, well, it'd be 24 divided by 400. So that's going to be our 0.06. So it must be going through this point here when we've got a 12 volt potential difference across it. But we know that the resistance, and the resistance of this is going to be 1 over the gradient, and the resistance is dropping as the voltage is increasing here. So we're going to have a graph which is looking like this, which is ever increasing going through this point here. So as the gradient of this graph, because we've got I on the y-axis and V on the x-axis, as this gradient is increasing, because our I over V is 1 over R. So this gradient increases, our resistance is dropping. So that's what's happening here. And that was what we had when the temperature was going up over here. So we don't have a straight line. So we don't have a constant resistance because the gradient is continually changing. So that is what makes this non-ohmic, because the gradient is changing. It doesn't change the validity of V equals IR. V equals IR will apply to any point, excuse me, on the curve. So if we picked this point here and took the gradient of it, or 1 over the gradient of it, then we would have our resistance. That is what we're going to get. It's going to fix there. So either, well, you don't really need to take the gradient. You just read the two numbers off, and then do the ratio of those in order to get 1 over the resistance. So we can just read those off. This formula always applies. Is the resistance constant? That is the thing that determines whether something is ohmic or not, and whether it's obeying Ohm's law. So there you go, basic circuit analysis, and then a few little clarifications at the end of it all.